Can anyone tell me, just based right here on the title, what is a titration? Because that's actually what you're going to be doing tonight. What does that mean? Anybody?
Isn't it the equivalent amount of like the reactants being mixed?
It does have something to do with reactants being mixed. So what is it you're trying to determine when you're doing a titration? Yes, Karina, you're determining concentration. That's right. So basically, when you do a titration, you have a solution of known concentration, and you're using that to calculate the concentration of an unknown solution. And you're doing that by knowing what the reactants are, how they react with each other, and we need something to tell us when the reaction's over. What are we going to be using to determine when our reaction's over in this experiment?
Sodium hydroxide.
That's one of our reactants.
Oh, is that phenolphthalein? Yeah,
right.
there you go.
And what does that do for us?
There's a color change, right?
There is a color change, exactly. So what we're going to be doing tonight is taking a solution of acetic acid. And so we should know by now, hopefully, that acetic acid is a weak acid. And we're going to, a dilute solution of acetic acid is just vinegar. And so what we want to do is calculate what the actual molarity of the acetic acid in the vinegar. And then we're going to use that information to calculate the percent by mass. Now remember, that means the mass of the solute, which is what is dissolved in the solution, the minor component of the solution, over the mass of the solution itself, times 100. And you probably noticed that on the vinegar you have at home, or the vinegar that's in the kit, the percent mass is 5%. So if we do everything correctly, we should get a percent mass of around 5%. So how do we determine the concentration of acetic acid if we don't know what it is? Well, we use the mass or the concentration of a known concentration of a solution that we know reacts with it. And what reacts with acids?
Base.
Bases, right. So if I have an acid plus a base, what are my products going to be usually?
Water and something else.
Water and salt. Water and salt, because generally the acid, remember, the acid, when it's neutralized by base, will release its conjugate base. And the base usually has something like sodium hydroxide or potassium hydroxide or something like that. So the sodium or the potassium will then join up with the conjugate base of the acid. And does anyone know what's the conjugate base of acetic acid? Who's actually read when acetic acid gets neutralized by hydroxide, what does it become?
Sodium acetate?
It becomes acetate. That's right. Acetate ion is the conjugate base. And so so we're going to learn how to calculate all these concentrations. We're going to be able to calculate the concentration of acetic acid. We're going to be able to calculate the concentration of the conjugate base, the acetate ion. And we're going to be able to use that to calculate the pKa of acetic acid. And we'll go over pKa's in a minute. So we know that acids produce hydrogen ions. Oops. Hydrogen ions when they dissolve into water. We can also refer to them as hydronium ions, basically the same thing. And when you dissolve strong bases into water, they produce hydroxide ions. And so when we want to measure the pH of a solution, it's going to be based on the concentration of H plus or H3O plus. It's exactly the same thing. Now we know that the pH scale ranges from 0 to 14. It actually goes higher and lower than that. But generally, most of the acids and bases that we'll be dealing with, there's also super acids and super bases whose pH will be greater and less than 0 and 14. But the ones that we deal with, we range from 0 to 14. So solutions with a pH greater than 7, we consider them basic. So because you remember that the pH is based on minus log of the concentration of H plus. So since it's the minus log, the smaller that the concentration gets, like 10 to the minus 9 molar, the smaller that concentration gets, the higher the pH goes. So remember that this is always, once the number goes up, it means you're getting less and less and less and less H plus ions. And since this is a log scale, every change of pH of 1 is 10 times the change in concentration of H plus ions. So the pH change from like 3 to 4 may seem like a small change, but it's actually a lot. That means there's 10 times less H plus ions in that solution. And we'll see that during our titration tonight, the pH changes dramatically. So how do we, hopefully everyone either has a calculator that can calculate logs and negative logs or inverse logs, or I'll just put the name of the website that has a scientific calculator. I'll just put that in the chat and you can use that, because we're going to have to do that tonight, because we need to be figuring out basically what's the concentration of H plus, and then turn that into pH, and then do the opposite. Take the pH and turn that into concentration of H plus. So we have to be able to do both. So this titration, we're talking about a titrant, which is what's known. That's the concentration. That's the reactant that we know the concentration of precisely. And so the analyte, what we're analyzing, is something that we don't know the concentration of. And so when we're doing a titration, when you're doing any acid-base reaction, we always need the balanced equation, right? We definitely have to have the balanced equation. So here is the acid. This is acetic acid, and it has one, what we call titratable proton on it. that is the H plus that gets released, this one right here. So in the presence of a strong base, like sodium hydroxide, it's able to pick off all of those protons during the titration. And so for every mole of sodium hydroxide we add, we get a mole of acetate ion. So this is sodium acetate right here. So that's the salt part of the acid base. And the other product is water. So what's the mole ratio of acetic acid and sodium hydroxide here? Based on that equation. So the molar ratio between the acid, the acetic acid, and the sodium hydroxide, what's the molar ratio between them? I've got too much junk here. Right, it's this equation right here. This is the acid. This is the base. What's the molar ratio?
One to one.
1 to 1, exactly. So we need that information to figure out, because we're going to know how many moles of sodium hydroxide we've added. We need to know what the ratio is to figure out how many moles of acid there is, and they'll be the same because this is a 1 to 1 ratio. So for doing this sort of titration, we would, if we were in the lab, we would be using something called a burette. And this is what a burette looks like. It's this long, skinny tube that we fill up with the titrant. Oops, let me go back. We fill up with the titrant. In other words, we would be filling it up with the sodium hydroxide solution. And then we use this stopcock down here to open it up and allow liquid to flow down. And so we fill it up, unlike most things we measure volume with, like the graduated cylinder. You'll notice that we start with 0. And then as it goes down, we get bigger and bigger volumes till we get to 50 ml. So notice what it says on the label here. Do you remember when we looked at the graduated cylinders and other things we used to measure volume? They had TD and TC written on them. Do you remember what those meant? Some said TC and some said TD and TC. TC means to contain, if you remember that. What did the TD stand for?
To deliver.
To deliver, exactly. So this particular piece of equipment is not designed to contain a certain volume, because we can fill it up to whatever volume we want and then measure what the volume was at the beginning and then what the volume was at the end, and then subtract the difference, and that's the volume it delivered. So it is designed to deliver a very precise volume of titrant, generally, and you can see here, plus or minus 0.1 milliliters. So you get very, very precise measurements. We are going to be using a syringe. So we won't have nearly the precision, but you will find that if you do this experiment carefully, you will get like, really, really good results with it. Like for instance, I think last week I was doing the experiment with the other class, and we got 5.1% mass. So that's pretty close to 5, if you ask me. So you can get excellent information. Not quite as good as it would be with a burette, but we make do. So this is what, if we measured the pH during our titration, you see that we get dramatic changes in the pH the closer and closer we get to the equivalence point. And the equivalence point is the point at which the moles of base precisely equal the moles of acid. So right at that point, and you can see just before we get to the equivalence point, the pH is acidic. So here we have the pH is less than 7 as we get before the equivalence point. And then after the equivalence point, the pH is dramatically different. It gets much, much more basic. That's because before the equivalence point, there is more acid than base. So it's acidic. After the equivalence point, there's now more base than acid. So the pH dramatically goes up, because if you remember, the pH is a log scale, and we're dealing with really, really, really small concentrations, like 10 to the minus 9 and 10 to the minus 8. Those are really, really small concentrations. So just one drop past the equivalence point, and the pH will be like 12. It'll go from 7 to 12 with like basically 1 or 2 drops of liquid. So we have to be really, really careful that we don't add too much too quickly when we're doing this reaction. So that's the equivalence point. The end point is what we basically estimate the equivalence point to be, because it's basically impossible to get exactly the equivalence point. Because at that point, you would have exactly the same number of moles of acid and exactly the same number of moles of base. And that's basically impossible to do. You can get really, really, really close, but you can't get it exactly to like, 6 significant figures. You're going to be off by a little bit. And so generally, we're going to be adding just a little bit more base than we should. And that's not an error. There's really nothing we can do about that. And that's why we use the phenolphthalein. The pKa of phenolphthalein is 9, which means basically it goes from an acid to a base at pH 9. And what color is phenolphthalein in an acidic solution?
Clear.
Yeah, it doesn't have any color. And what color is it when when it's in a basic environment and becomes a base?
Pink.
Yeah, it turns pink, or you'll see actually it's sort of pink or even like a bright red color. If you go way too far, it turns bright, bright red. And so what we want while we're doing our titration is for the solution to just turn a little bit pink, and then we're done. So what will happen when you add the base into the solution, you will notice that the solution will turn pink where the sodium hydroxide is dropped in. That's because the local concentration of hydroxide in that solution will be very high. And so that phenolphthalein will turn pink. But then when you swirl it, the color will disappear because you will have mixed the hydroxide into the solution, and you'll no longer have a high concentration of hydroxide in one particular place. It will be diluted, and then the pH will go, of the whole solution will go back to being acidic, and so it'll become clear. So what we want is, as we're swirling and swirling, it'll take longer and longer and longer for that color to disappear. So when we get to that point, we want to basically be adding drop by drop by drop, okay? So if you remember, we talked a little bit about Ka. That's a dissociation constant. And dissociation constant refers to this reaction. Here's my acid, my weak acid. And so H just stands for the H plus, and A stands for the anion that it is attached to. In our case, it is acetate. Now, when it dissociates in solution, it releases H plus and acetate. But this is a weak acid, and so this reaction does not go to completion. A strong acid like HCl, when we put that in solution, all of it goes to H plus and Cl minus. And so this arrow only goes in one direction. But acetic acid is weak, and so it's H plus and acetate goes backwards and reforms acetic acid. So that's why the arrows go in both directions. And so this reaction of acetic acid leading to H plus and A minus. This is governed by what we call the equilibrium constant. It tells us how much H plus and A minus is going to be. And so that is determined by what's the concentration of H plus, what's the concentration of acetate, divided by the concentration of acetic acid. And that equals the Ka. So you can see that the lower the Ka is, the less H plus and A minus you make. The higher the higher the Ka is, the more H plus and A minus you make. So really, really weak acids have very, very low Kas, and stronger acids have higher Kas because they make more H plus and A minus. We use pKa, which just stands for minus log Ka, because these numbers are really, really, really small. Like 10 to the minus 5, 10 to the minus 7. I mean, like really, really small numbers. And so it's just easier to use the minus log. So 10 to the minus 5, the minus log of that would be 5. 10 to the minus 7, the minus log of that would be 7. And this breaks down into this equation. This is a misspelling. It's the Henderson-Hasselbalch equation. There's no L in it. So the pH at any one time when we have a weak acid is the pKa of that particular acid plus the log of the concentration of the conjugate base over the concentration of the acid. And we're going to be using this to determine our pKa of acetic acid. Now, when the concentration of A minus and the acid is the same, this ratio is 1. What is the log of 1? 10 to the what power equals 1?
Ten to the 0? Or is
That's
it
right.
10?
10 to the 0. That's right. And so this becomes 0. And at that point, the pH actually equals the pKa. So halfway, the midpoint of the titration, halfway through the titration, we should have turned half of the original acid into conjugate base. So exactly half of the original acid will have turned into base. So at that point, the concentration of the conjugate base, A minus, and the concentration of the acid that's remaining, HA, should be the same. And then at that point, the pH should pretty much equal the pKa. I will go over this calculation with you in a minute. I just want to make that clear. So let's just have a look at what that means. So again, here's our Hassel-Balch equation. So when my conjugate base equals the concentration of my acid, then this drops out and the pKa will equal the pH. These two will equal each other. So look and see when that happens. So if that happens, that should be halfway to the total. So the total base added is 25 milliliters. That's the equivalence point. So at that point, all of the HA has been converted to acetate, all of it, because the hydroxide has peeled off all of the protons from the acetic acid and turned all of it into acetate. At the beginning, there's very little acetate produced. There's some, because it's a weak acid, it will be releasing some acetate, but very, very little. So at the beginning, there should be very little acetate, very, very low. At the end, it should be all acetate. So in the middle, at around 12.5 mils, right there, half of it should be turned into acetate. Half the acetic acid, HA, should be turned into A minus. So again, this is a weak acid, so that's not exactly true, because some acetate has been released before any hydroxide has been added, because it's a weak acid. It's going to do that. And you can see that from the pH at the beginning is 3. So some H plus has been released, and acetate as well. So it's not going to be perfect, but the pH at halfway should be really, really close to the pKa. And we can see here that this is around 4.8 or so, a little less than 5. So it's somewhere between like 4.5 and 5, but really close to 5. And the actual pKa of acetic acid is 4.75. So that's really, really close. So we're going to be using this to determine the pKa of acetic acid. Hopefully we'll get fairly close to 2.75. Any questions so far? We let them go, and I'm blathering kind of quickly about this. Is everyone comfortable with the idea of Ka, what that means, and pKa? P just means minus log. Whenever you see a P in front of something, that means take the minus log 10. Like pH means minus log 10 of H. pKa means minus log of Ka. That's all that P means. So we have to get familiar with logs and inverse logs to be able to go back and forth. All right, I'm just going to keep blathering if I don't hear any questions. So this is the stuff we're going to be using tonight. So we need a graduated cylinder, make sure the Erlenmeyer flask is clean. I made a mistake last week. I hadn't cleaned it beforehand and had something in it. And instead of turning pink, my solutions turned blue, which was interesting because they weren't supposed to do that. So there was something in there. I think it was copper. I still had some copper in there, and the acid base reaction turned it from green to blue. So that was fun. Some plastic cups, our balance. You're going to need the syringe. Hopefully everyone's found the syringe, and you get some vinegar. Need it, but not supplied. Some kind of vinegar sample. It doesn't, pretty much the only vinegar that won't work is red wine vinegar for more or less obvious reasons. Why won't red wine vinegar work well? White wine vinegar will be fine. Red wine vinegar, not so much. How come?
The color.
Yeah, it's the color. Basically, it's already the color we needed to turn. So that's not going to really work so great. This is going to be our titrant, 1 molar. We're going to treat it as a 1.0 molar solution. So we'll use 2 significant digits for the concentration. And then this is our indicator. Why is it called an indicator?
It helps indicate whether it's an acid or base.
Yeah, it indicates the change in pH. It indicates the reaction is taking place. So any reaction we do, basically we need, if we're doing a titration, we need to know exactly when the reaction is over. And so we need something to tell us that, or we're just going to keep adding more and more hydroxide because we don't know when we've titrated all of the acid. So we need an indicator to tell us that. And so that's what we use the phenolphthalein for. In the lab, we could use an actual pH meter and measure very precisely what the pH is and then see it move. But if we don't have a pH meter, then we use something that changes color to let us know. So this is how we're going to get started. Basically, we want about 5 mils of vinegar in a graduated cylinder, and then get the mass of the vinegar. So you put the 10 mil graduated cylinder on the balance, tare it to 0, add around 5 mils of vinegar. Doesn't have to be very accurate, because what we're going to be doing is measuring the mass very precisely and then turning that into a volume. How are we going to do that? How do we take the mass of something and convert it into a volume?
The molarity.
Nope.
Oh, I mean like you know, the mole liter relationship.
Nope. It's nothing to do with moles. If I have a liquid and I measure its mass, what do I need to then determine what the volume of it is? What's the
Density.
relationship between mass and volume?
Density.
Density, exactly. So we know precisely what the density of vinegar is. I think it's 1.005 grams per ml. So we're going to use that to take our mass and convert it into a volume. So we'll have a very, very accurate volume. Then we're going to put hydroxide, and we're going to put that, it's in a drop bottle, so you're going to have to squeeze it pretty hard to get the liquid out into one of the small cups, and then draw up the sodium hydroxide with the syringe, attempting to minimize the amount of air, like the smallest amount possible. So you record the initial volume on the syringe to the nearest 0.1 mils. And then we measure the volume when we're done, again to the nearest 0.1 mils, subtract, and that will be the volume of sodium hydroxide added. So now we're going to have the volume of hydroxide. We'll have the concentration of hydroxide. We'll have the volume of acid. And then we use that to calculate the concentration of the acid. So we're going to be adding hydroxide in about 1/2 ml increments at first, like 1/2 ml, then swirl, 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 1/2 ml, swirl, swirl, swirl. You're going to want to have the flask with the vinegar in it against like a white background to make the color change much more obvious to see. If you have like a dark background, you're really not going to be able to see it. So have like a piece of paper, some white paper to be able to see it better. So the color change should look, I mean, the perfect titration, you would have a color change that looked like that. But that's really not going to be possible for us for a number of reasons. One, we're using a syringe, and it's very difficult to add like a 1/4 drop, a 1/2 drop that you could if you had the burette. The other thing is that this volume is much greater than what we're going to be using. We're going to be using a really small volume, like around 10 mils. This is about 25 mils. And so our color is going to be more intense than this. So what we're going to be looking for is more likely a color that looks like this third flask from the right. So this pretty much the color we're going to be looking for. If we get something darker than that, we've probably gone way past the titration point or the equivalence point. And so we might want to do it again. These experiments don't really take a whole lot of time to do. You'll see the first one takes a long time because we want to be really, really careful. The second time we do it, we're going to be doing these in triplicate. The second time we do it, we're going to have a pretty good idea of the volume we need. So we can get to that volume fairly quickly and then slowly go drop by drop. But that first one you do should be really, really slow and careful. I mean, they all should be careful, right?
Did you want us, it says to take pictures.
Mm-hmm.
Did you want us to do that?
Yep, before and after. It's in, remember, to use the template that's provided. That's why we provide it for you guys to use it. Yeah, so you want a shot of the, and you don't do it every time. Like basically do your best one. If you have like a really good one with a really pale pink color, that's the one to use. So a shot, before and after shot, basically, before you added sodium hydroxide and at the equivalence point. Or for us, the end point.
And these pictures you want us to put in the lab report.
Yep.
Okay.
Yeah, so basically, we're going to be adding the hydroxide drop by drop with constant swirling until a single drop causes a color change that persists when we're swirling. And when that's done, we're done. We've reached the end point, and then we calculate the volume of hydroxide we've added. Okay, so then we take the pitcher. We want to rinse the flask 3 times and then basically repeat it 2 more times. So you do it with the vinegar that's been provided, and then 3 times with a vinegar of your choice, white wine vinegar, apple cider vinegar, whatever it is, rice vinegar, whatever it is you have. So here, when we calculate the concentration, let's say, for instance, we calculate oops, I want white for this. Forgot. Let's say we that's white. Let's say we have a calculation or concentration of 0.800 molar acetic acid. So how are we going to figure out what the mass percent is. So we have the molar mass is 60.05 grams per mole. And so 0.8 moles per liter times 60.05 grams per mole gives us gives us 48.04 grams per liter. Now remember that the density of the vinegar is 1.005 grams per mil. So that means, how much is my liter going to weigh? What's a liter of vinegar going to weigh? If it's 1.005 grams in 1 ml, if I have 1,000 ml, what's the mass going to be? One ml weighs 1 gram. How much is 1,000 ml going to weigh?
1,000 grams.
And if it's 1.005 grams, how much is 1,000 mils going to weigh?
1.005
Unit?
grams.
Nope. It'll be 1,005 grams, right? Because we multiplied this by 1,000. So 10, 100, 1,000. So the entire solution will weigh, one liter of solution will weigh 1,005 grams, of which 48.04 grams is acetic acid. So that is my ratio. We multiply that by 100. And we get 4.78%, which is pretty close to 5. So that tells you that the concentration you should be getting for acetic acid is around 0.8 to 0.9 molar, somewhere in that range. Pretty close to that. I think the exact concentration is 0.885, something like that. So you're going to want to have it just a little less than 1, actually a little less than 0.9, and you'll get a mass percent of around 5, which is what we're looking for. So the data table, the first data table, just basically just put in what each time what the mass of vinegar is. It should be around 5 grams, and then calculate the volume from that. What was the initial volume of sodium hydroxide in your syringe? What's the final? Calculate how much you actually delivered. What's the difference? And since that's 1.0 molar, how many moles did you titrate with, which should equal the number of moles of acetic acid in your sample? Calculate what the mass of acetic acid is in your sample based on the 60.06 grams per mole. Figure out what the molarity is based on the concentration, and then calculate the percent mass. And so your average of the 3 should be around 5%. And then the same thing for the second table. Table 2 is basically exactly the same, but with different samples. So I want to talk about table 3 because some people were really confused about that. Because table 3 is based on not your experiment, but an experiment somebody else did using a pH meter. So here you can see they're using a pH meter to measure the pH of another titration of vinegar with sodium hydroxide. And they're using a burette this time. So more accurate measure of volume. So this is what the original burette reading is. This is what the final burette reading is. And so how much they actually delivered would be the difference. So that would be the volume of sodium hydroxide dispensed. In this particular example, they're using 0.1 molar sodium hydroxide, so 10 times less concentrated. And they added 21.05 mils of acetic acid sample. So based on that, you can calculate the molarity. Now, they're using dilute vinegar. So their concentrations are going to be different than what we're doing, about 10 times more dilute. Now, you're probably wondering how we're going to calculate the pKa. So I will show you. All right, so here's the part where we're calculating the pKa. So I'm going to go over vinegar sample 2 with you, and then you can do vinegar sample 3 by yourselves. So this is the information we have. The volume of acetic acid is 21.05 mils. The concentration of hydroxide is 0.01 molar. So now we look and see what the initial burette reading was. It was 3, and midway through the titration, this was the burette reading. So the volume of hydroxide midway is 12.92 mils minus 3.00 mils, or 9.92 mils. So that's important for us to figure out. At the end, so the volume of hydroxide at the end point is equal to 20.31 mils minus, again, the 3 mils that was at the beginning. So 17.31 mils. So we need to figure out what the concentration of acetic acid is at the beginning, before we haven't added anything. We get that from the volume of hydroxide at the end times the concentration of the hydroxide. That tells us what our initial concentration of acetic acid was. So this is the volume. So 0.01731 liters, we have to convert it to liters, times 0.1 molar, which is moles per liter. So the number of moles of acetic acid at the beginning was 0.001731 moles. You with me so far? Yes, no? Okay. Just, unless I hear from you, I'm going to continue this confusion. So that's how many moles of acetic acid I have at the beginning. Now, I need to figure out how many moles of acetic acid I have at the midpoint So remember, at the midpoint, the volume of hydroxide was 9.92 mils, which is 0.00992 liters. Well, if I multiply that by 0.1 moles, man, wish this worked better, per liter, the moles of hydroxide at the midway point is 0.000992 moles. That is the moles of OH minus. It also happens to be the number of moles of acetate, or A minus. Why is that? Why does the number of moles of hydroxide ion equal the number of moles of acetate? Why is that?
It's a 1-1 ratio. If you look at the chemical equation.
Right, if you look at the equation, OH minus is a reactant and A minus is a product. And so for every mole of hydroxide ion we add, we get a mole of acetate ion and a mole of water. That's the reaction. So basically, what we're doing is we're converting a strong base into a weak one. That's why the pH only goes up slowly, because we take a very strong base and we're converting it into a very weak base. So a weak base doesn't really change the pH very much. But when all the weak base is basically used up, then we have more strong base than weak base and our pH rockets up. So if this is the number of moles of acetate ion halfway through, well, where did that acetate ion come from? It came from this many moles of acetic acid at the beginning. So the number of moles of acetic acid that are left must be the difference. So this is the number of moles of acetate ion halfway through. So the number of moles of acetic acid halfway through must be 0.01731 minus 0.0000992. And that equals, luckily I've done this already, 0.000, see, small numbers, 739. So you can see that it's a little less than half. I have a little more acetate than acetic acid. And the reason for that is this isn't exactly midway. That's an estimate of what midway is. When you're doing the titration, you don't know exactly where the midway point is, because basically your final reading is only an estimate of the actual end point. The end point is actually different from the equivalence point. The equivalence point is the actual spot where moles of acid equal moles of base. The end point is where you estimate the equivalence point to be. So it's going to be wrong. So this isn't quite halfway, but it doesn't matter, because as long as we can calculate moles of acetate and moles of acetic acid, and we have the pH, we can figure out the pKa. So let's do that now, because now we have all the information we need to calculate the pKa. We have moles of A minus and we have moles of HA. And so we're going to use that to calculate the pKa. So let me clear that. So remember, the Henderson-Hasselbalch equation was pH equals the pKa plus the log of A minus, in this case acetate, over HA, in this case acetic acid. And so we can rearrange this. What was the pH at the midway point? 4.895. So 4.895 equals the pKa plus the log of, now I'm going to use moles of A minus and moles of acetic acid. Why doesn't it make any difference if I don't convert them to concentration? How come I can use moles instead of concentration? Why doesn't it matter?
Are they the same?
What's the same?
Um,
Concentration isn't the same as moles,
oh,
but something is the same. I mean, you're
was
right
it,
when you say it's the same, but what is the same?
um, was it the, is it like that 1 times 10 to the negative 14 power?
Nope.
Number?
Nope. Doesn't have anything to do with that. Why does moles of A minus over moles of HA equal the concentration of A minus divided by the concentration of HA? Why are those two things the same?
The 1-to-1 ratio in the chemical equation?
Nope. So keep going, you're gonna get it. I know you're gonna get it eventually. So come on, somebody else guess. I mean, come on. What is, just think about what concentration is. What is the molar concentration? What are the units of molar concentration?
Moles over liters.
Right.
And since we know moles, we'd be able to find out the liters, won't we?
We don't need to.
Không mà cái đó
Why don't we need to?
đúng không?
Yeah, the reason is they give you the same number, because if I take moles over moles of A minus and divide it by some volume, and then I take moles of HA and divide it by some volume, these things cancel. The volumes cancel out because the volumes are the same. The number of moles of A minus and the number of moles of HA are in the same volume. And so the volume cancels out. So we only need moles. If you have the concentration, that's nice. You can use the concentration. But if you, it doesn't matter what the volume is because the volume is the same. So if we're dividing both moles A minus and moles of HA by the same volume, the volume cancels out. So I'm fine with using moles. So if you wanted, you can use moles or you can use concentration, either one. But the moles have to be in the same volume for that to work. So this is one of those shortcuts where you need to know what you're doing or it won't work. But if you have the same volume in each case, then when you divide one by the other, you'll get the same answer. So I need the log of 0.000. So this is my A minus, 992 moles divided by 0.0000739. So that's my moles of acetic acid at the halfway point. So this, we look up, that would be log of 1.3424. And so you just plug that into your calculator. Basically, what is 10 to the 1.3424? And the answer is 0.1279. So this is, and this should always be a pretty small number, 0.1279. You should not get a large number here. It can be negative, it can be positive, but it should be small. So now I subtract this from both sides, and 4.767 equals the pKa. So this is my pKa. So like I said, the actual pKa of acetic acid is 4.75. So this is really, really close. So did everyone get any of that? I can make another video and post it.
Yeah, that'd be good because I'm like completely lost.
Yeah, because I think the last people, the group from Thursday, a number of them have told me they're still working on this table 3. So I think maybe that's what I'll do. So
So
we'll have this, and I'll make a video just on this alone.
Are you giving us so we only need to do vinegar sample 1 and vinegar sample 3? Is that what I'm getting?
Well, and 2 as well.
But aren't you giving us 2?
Well, I'm going to need to see the calculations.
Oh, because I thought everything that you were describing now was pretty much what vinegar sample 2 was.
It is, but I need to see your calculations.
Or is this more of just, hey, this is how you do it?
It's both.
Oh, okay.
This is
I'm still really lost, but okay.
This is how you do it. Yeah. Okay. So I am going to give everyone like 5 minutes to get all their stuff ready. And then we'll come back. Goggles on for this one, because we're dealing with sodium hydroxide. So we really don't want to get that in your eyes, because that will blind you. If you get some on your skin, just stick it under the tap for like, a good few minutes and wash it off. But yeah, you probably don't want to get it. You probably don't want to wear nice clothes either, because it will eat through your clothes.
This might be a stupid question, but what happens if you accidentally consume it?
It'll burn the inside of your mouth.
Oh.
Yeah. Yeah, basically it'll dissolve. It dissolves things. That's why it's worse than, that's why I think anyway, it's worse than acid. Acid burns, but hydroxide dissolves. So, I mean, it also burns too, but it does a better job. One of the things we'll learn later about organic is that bases are much better at dissolving organic material than acids are. So that's kind of nasty.
Is that why we use bases to clean stuff like bleach?
Mm-hmm.
Or is it because bleach has a tendency to like rip the electrons away of like organic stuff,
Yeah, actually it donates electrons.
Oh.
Yeah, when we, I can't remember if we do
It was oxidation,
reactions
right?
or not.
No, I don't think so. Oxidation, I know, is loss of electrons, and then
Yeah.
the
Bases
reduction is gain.
reduce, they add electrons, acids take electrons away.
Oh, I see.
All right, so 5 minutes, we'll come back and we'll get started, okay? Make sure you have everything together and goggles on. So I'll see you in 5. So goggles and cameras, people. So we want our so here's our 10 mil graduated cylinder. And we tear it, so it's 0, 0, 0. And so you want to transfer the vinegar with one of these with a transfer pipette like this one. You should have those in your kit. Now remember, yeah, you don't have to get 5 on the nose, because we're going to be measuring the mass anyway. but pretty close to 5. If you fill this thing like pretty much one big squeeze, it gets you about 3 mils or so. All right, so 5.21 grams. Write that down. So I transfer that to my clean, and I can't emphasize this enough, clean 25 ml flask. Because tonight you will see why flasks have this particular shape. There is a reason for it. And you can just give it a little tap, make sure you got all of it. Here's our phenolphthalein, and you don't want to drink this. This causes diarrhea. So it's kind of nasty. So 1 drop is good. Oop, I got 2 by accident. Oops. Swirl it around, and it should not change color. So it should, there's your before picture. And you could remember, you want to photograph this against a white background. I've got white paper here, so that works nicely. But if you have like a dark background you're working with, you're going to want a white piece of paper. So small cup like this, and we're basically going to, about halfway with our sodium hydroxide. Here's our 1 molar sodium hydroxide. And it says careful, and you should. Audrey got her gloves on, but no goggles. What the hell? I can rinse, base off my hands a lot easier than I can wash it out of my eyes. You know what I'm saying? This is kind of tough. You got to squeeze, give this a really hard squeeze. And it's going to take a while. If your hand gets tired, you can use both hands. You can use the other hand. Okay, that'll be enough. So this here's 10 ml syringe, and you can see that there are 5 marks in between each mil. So it's going to be kind of tricky to get 0.1. 0.2 we should be able to, 0.2 mils we should be able to get. So anything in between, remember these are 0.2 millimeter or 0.2 milliliter increments. So remember that when you're measuring your volume. They're not 0.1. And we just draw it up. Do not worry if you have less than 10. Doesn't matter. As long as you have like around 6 or 7 mils, that's fine. If you have if you have bubbles in there, you can just smack and just push them out. So now I don't have any bubbles. And then the volume you want to measure is where that top piece of rubber is, not the bottom. So this, what is this? So that would be about 9.4 mils. I don't know if you can see that particularly well, but you want the top piece of rubber, not the bottom. So I've got 9.4 mils. So that will be my initial volume. Remember, at first we deliver in, what size increments do we deliver in at first? Who remembers? Hi, Megan's dad. So what size volumes do we add at first? No, Karina's reading the instructions. What do you get? ½ mil. So about ½ mil. So the way you do not want to dispense like this, pushing down, what you want to do is just push basically just a little bit at the base. Don't push from the top. That's just a little bit at a time from there. Sort of a gentle squeeze rather than. And what you should see is that, I don't know if you can see that, but it turns pink as I'm adding it. Here, I'll put it up to you'll see the same thing. But when you add it, it turns pink. See that? But then when you swirl it, it goes clear again. So that's what I was mentioning before about the local concentration of hydroxide will be high in very small parts of the flask. But when you swirl them, you dilute the hydroxide concentration and the pH goes back down again. So now you can see why this is this particular shape, because when you swirl it, it doesn't come flying out the top. That's why flasks are this shape.
Do you want us to use flash when we take the picture?
Whatever it takes. I mean, I'd take a picture with and without, see which one looks better. I mean, you might get too much reflection if you're taking a picture of glass with a flash. Yeah, here you can see it gets really pink, and then just like magic, disappears. So you can see you can add it like just pushing very gently from the base. You can get like basically a drop at a time. Color and gone. So you see it's disappearing rather quickly. So that means I'm not particularly close to the end point. So I can continue to add about 4 or 5 drops at a time and swirl and disappear quickly. But when it starts to take like a couple seconds, then you're really close. Basically, you want to be 1 drop over. And if it's not disappearing, you're done.
Not disappearing when swirling, correct?
Yeah, then you're finished. But it shouldn't be like this really, really, really bright color. I mean, it's ooh, I'm getting close now. That one took a little longer. Yeah, so take your time. Like I said, the first one is going to take the longest because at this point you have basically no idea what volume it's going to take. The second time you do it, you'll have a pretty good idea of what volume it is to take. So you can go to a little less than that volume fairly quickly and then go drop by drop. Oh man, I am super close. Ooh, it took about 4 or 5 shakes. Oh, damn it, I went over. See, I went over. So I think I went like 1 drop too many. So yeah, you want a color that's a little less than that. That's pretty close, but it probably could have been better. I tried to add 1 drop and I added 2. So yeah, so I could swirl this all day and it doesn't change back. So now I'm going to read my volume. And that is 5, right on the nose. 5.0. So notice, so I want to show you something. I'm going to add water to this. If I add water to this, is the color going to change back to clear? What do you think? Bets, I got $5.
Yes.
Okay. You owe me $5. So this shows you that if we dilute this sample, it doesn't really matter. We could have done this titration in half the volume, twice the volume, 50 times the volume. It really doesn't matter. Why doesn't the volume matter when you're doing the titration? What is it we're actually titrating?
Is it because the molarity is high?
No, that's what is it? We're not titrating molarities, are we? What are we actually titrating? What's the actual reaction? We're not titrating molarities. Who's reacting with who?
The acid with the base.
Right. In what quantities are the acid and the base reacting with each other?
Wouldn't like the water be like a spectator or something like that?
It's not an ion. But what is reacting? What measure of acid and base is reacting here? What quantity are we dealing with? Is it grams? Is it mils? What is it?
Milliliters.
Nope. We don't balance milliliters in a reaction. What do we balance in a reaction? We have a balanced reaction. What's actually balanced in the reaction? What are we balancing? Come on, Cassandra, you got this.
I'm sorry, I was reading. What was the question?
What the acid and base are reacting in this particular reaction? In what quantities are they reacting? How much of acid and how much of base are reacting with each other? What quantities do we measure these in? What have we been talking about since class started? Starts with an M.
The moles.
The moles, right. It's moles of base react with moles of acid. So it doesn't matter what the volume is. The titration will take place at exactly the same amount of acid and base. It could be in 10 mils, it could be in 50 mils, it could be in a liter. It doesn't matter because it's moles interacting and reacting with moles. The volume is irrelevant.
Sorry, I wanted to ask you how, okay, when you get the sodium hydroxide in the syringe, where's the point that you measure? Is it where the pointy end is?
You measure where the second piece of rubber, the piece of rubber closest to the end.
Oh, so not the pointy end then.
What?
The thing that looks like a pyramid?
The thing that looks like a pyramid.
I don't
No,
know what you,
this rubber syringe tells the rubber part of the
oh, okay.
stopper. That tells you where the volume is.
Not
So
the one
this-
closer to the one that says midline, but the other one.
So this is 5 mils. You can see this top piece of rubber is right at the 5.
Oh, okay.
And then you make your best estimate. If it's a little less than 5, it's a little greater than 5. And remember that these are in 0.2 mil increments, not 0.1. That's an easy mistake to make because most of the time we deal with like 1/10 increments. This time we're dealing with 1/5.
And did you want us to push the liquid all the way to the top of the syringe? I don't know.
No,
how to
it
explain
doesn't.
this.
You don't need to have. It doesn't need to be to the very top. As long as you have like around 6 or 7 mils in there, you're fine. Because the volume you're going to need is roughly equivalent. Because remember, the concentration of the vinegar is around 0.9 molar. We're titrating with 1.0 molar. So the concentration of these two is pretty close to each other. And if the concentrations are close, the volumes are going to be close too.
Like, I don't know if you want me to move it all the way to the top over here, or if it's enough to be right here.
Oh, the top. Well, you're going to
Yeah.
be filling it from the bottom. You put the syringe in like this and you draw it up. So there should be liquid in there.
Right, it is.
Okay.
I just wasn't sure, in terms of getting the amount of air, if you wanted it to be all the way to over here where there's the liquid right on the like top here, or if it was enough for the liquid to just stay at this point.
No, it's got to be out.
So all the way here.
Yeah.
Oh, okay.
Okay. but I'm going to move back and do some calculations here.
So would this be 9.9? It's between 9.8 and 9.9. But it's not exactly at 10.
I can't see it, Vera.
Oh. I don't know how to. Is it?
If it's, yeah, I mean, if it's a little less than 10,
Yeah.
if it's exactly on the increment below it, that would be 9.8. And if it's in between, it would be 9.9. Because
Okay.
those are 0.2 mil increments.
Okay.
So if it's in between, yeah, call it 9.9.
Okay.
All right, so I had 5.21 grams of acetic acid. My initial volume of hydroxide was 9.4 mils. My final volume was 5 mils. So I delivered 4.4 mils. So the first thing I'll do is convert my mass into a volume. So that's my mass. And I want to convert it to mils. And I know that 1 mil is equal to 1.005 grams. So that gets rid of grams, and I'm left with mils. And the reason we do this is we can measure mass much more precisely than we can measure volume. So we take advantage of that. And so my volume is 5.184. And remember, I'm going to carry as many digits as I like through my calculations. You can report 5.18 mils, but I'm going to carry that 4 just because, well, because I can. So 5.184 mils. So my volume of hydroxide times the concentration of hydroxide is going to equal the volume of HA times the concentration of HA. So I believe it asks you to calculate the number of moles of hydroxide. Is that correct? I think it does, right? So if I need to calculate moles of hydroxide, I need to convert this to liters, because that is what my concentration is in. So there's 1,000 mils in 1 liter, so that's going to be 0.0044 liters. So that is going to put that as my volume. Remember, the concentration is 1.0 molar, or moles per liter. And since it's 1, the number of moles are going to be equal to the volume in liters, because it's 1 mole over 1 liter. So my number of moles of hydroxide is this. So moles of hydroxide, 0.0044 moles. So if that's my moles of hydroxide, how many moles of acetic acid did I have?
One to one, I believe.
Yeah, 1 to 1. It's a 1 to 1 ratio. Exactly. So if it's a 1 to 1 ratio, I have the same amount. That's the same amount of moles of acetic acid. So moles of acetic acid also is the same thing. So now I can calculate the concentration because I have moles, I have a volume. Moles over liters is molarity. So that is 0.0044 moles times 5.14 mils times oh, wait a minute. I want 1 over volume. Idiot. Times 1 over 5.184 mils. And then convert the mils to liters. Times 1,000 mils is 1 liter. So now I get rid of my milliliters and I'm left with moles on top, liters on the bottom. That is what I want. Zero point 849 moles per liter for molarity. My molarity is 0.849 molar. So now I'm going to use that information to figure out my mass percent. So 0.849. Zero 0.849 moles per liter. That is what the concentration is. But I want grams of solute over grams of solution. So I need to convert the top to grams of solute, because this is moles of solute right here. And liters, that's the volume of the solution. So I do my first conversion by changing moles of solute to grams of solute. And I believe that was what, 60.05 grams per mole. Is that right? I think that's the molar mass of acetic acid. And now, so that gets rid of moles. So now I've got that many grams of HA. I still need to convert liters to a mass of solution. So I will multiply that again times 1 ml of solution is equal to 0.005 grams. And convert the milliliters to liters. 1 liter is equal to 1,000 milliliters. So my mils are canceled. And what I have now is, on the numerator side, grams of acetic acid, and on the denominator side, grams of solution. So let's plug that in. 0.849 times 60.05. divided by. So that equals 0.05073. Now remember, but you're saying, wait a minute, that's much less than 5%. But this is a ratio. Percent is when you multiply that by 100. That's your percent. So my percent is 5.07%. And since I have only 2 significant digits to my concentration, I narrow this to 2 significant digits, so 5.1. So you can see that's pretty darn close to 5. So even though I went like 1 drop over, I still got a pretty good result. 5.1%. I wouldn't feel too bad about that. So to put it in, so that would be, what would be my relative error with 5.1% when I was expecting 5?
0.0%, I believe. Is that
No.
correct? Oh,
So I was expecting 5% and I got 5.1. What's my percent error?
0.1%?
Nope. So
Or
my
was it the-
absolute error is 0.1.
Oh, and then you times it by 100, right?
No. I divide it by the expected. So this is my absolute error. When I divide it by the actual amount, I get relative error. That would be 0.02. So my percent would be 2%. That's a pretty good error. I will take 2% all day, especially when, you know, measuring with a syringe and everything else. So that's pretty good. All right, so because everyone's still working. So I will hang for a while if anyone has any questions. So I've recorded all of that, so you can watch it later.
And what
Anyone
you,
have any questions on like how to do the experiment? Cassandra's got a question. Oh, Cassandra's got a big boo face. What's up?
I'm just trying to follow along. So, in the last thing that you wrote in the equation that you wrote, I'm
Oh,
trying.
I can put that back up, I think. Hopefully it's still there. Yep, still there.
Yes. So 1.005 grams. Where does that come from?
That's the density. So let me clear some of this up.
This is molar mass. So 60.05 grams is the molar mass.
I think it is. Is that right? Because I haven't got it open in front of me. Is it 60.05? I think it is, but I can't remember precisely. It's around 60. Right, so this is the concentration of acetic acid in the solution. So we got that from our titration. So I need to turn this into grams of solute. And I need to turn the liters into grams of solution. Because that is this expression times 100 is my mass percent. So I turn the numerator into grams of solute by using the molar mass. So that was 60.06 or something like that, grams per mole. So that's grams of acetic acid. Now I need to convert the bottom to grams of solution. How am I going to do that? Well, I do that with the density. So I take the density of the vinegar solution, which is given to you as 1.005 grams per mil. Now I can just, since I want liters, I could just convert this right away to mass per liter. I just multiply both top and the bottom by 1,000, right? That would be equivalent to 1,005 grams in 1,000 liters. Well, I mean, 1,000 mils. Well, what's 1,000 mils? That's a liter. So if I have grams of acetic acid, then I want to multiply that by 1 over the grams of solution. And that's 1,005 grams. So I've converted liters of vinegar to grams of vinegar. And vinegar is my solution. So now I get rid of moles. And what I have left is grams of acetic acid on top and grams of solution on the bottom. That is my mass percent. So I just do the calculation. And it is 0.84, oops, 0.849 times 60.06. So that's 50.99 grams of acetic acid divided by 1,005 grams of solution. I multiply that by 100 and I've got my mass percent. 5.07%. And I round that to 5.1 because I only have 2 significant digits in my concentration. Actually, we really only have 1 because it says 1 molar, but I know the concentration is more accurate than that. So I think we could definitely assume that it's at least 1.0 molar. It's probably closer to 1.00 molar, but I don't know that for sure. So 2 significant digits, 5.1%. Okay.
For the 0.849, that was from the previous equation that we did, correct?
That was from my titration.
So I got 0.080. Is that completely off?
Moles per liter.
Yes.
Okay,
Does that sound completely off, or does that sound
that's pretty close.
okay?
Yeah, I mean, basically anything between 0.8 and 0.9, you're in the ballpark.
Okay.
I think the actual, well, I should just look it up. I can just look up the actual molar concentration. It's around 8.835 or something like that. I'll just look it up.
Professor,
But
for
this is
the
pretty close. Yeah.
for the volume of vinegar, so you just do volume equals mass over density. Did you want it in 2 significant digits because the sodium hydroxide is in 2 significant digits?
I'm sorry, what, the volume of the vinegar?
Yeah.
Yeah, well, the volume of the vinegar has nothing to do with the how many significant digits there are in the hydroxide.
No, I mean because you want the smallest number of significant digits
Where? In
for
the
the
table?
volume of the vinegar vinegar
No,
density.
that has nothing to do. That has nothing to do with the hydroxide. So you have 3 significant digits in your mass, and you have
Oh.
4 significant digits in the density. So your answer should have 3 significant digits in it.
Okay.
Yeah, don't round numbers before you have to. In fact, when I'm doing my calculation, I don't round at all until I'm finished, till I get to the very end. So if I have like, you know, if I divide 3 digits by 3 digits on my calculator and I get, you know, 8 digits, I just leave them there until I get to the very end, and then I round everything. Because if you start rounding things, basically you're losing precision in your results. So you don't want to do that.
And then to figure out the moles of like the base versus the acid, you just use the molarity of.
Right, you don't know what the molarity of the acid is. That's what you're calculating.
Oh,
So you figure out moles of base based on the volume and the concentration.
and you know how molarity is moles over liters, so
Yep.
we'd have to do it another dimensional analysis for milliliters, right?
Right, so you need to convert your milliliters to liters to get moles. That is correct.
Okay.
Yeah. Yeah, so the number you're going to get is small. It's not going to be a lot of moles. Very, very small.
Oh, okay.
Yeah, I think mine was like 0.0044 or something. Not a
Oh,
lot.
I see.
Yeah, not a lot.
And we're supposed to do this experiment 3 times, I think, right?
Mhm.
With 3 different vinegars,
No, the same one. You're doing in triplicate.
but one of them is a vinegar that you have at home.
Right, and you do that one in triplicate as well.
You do the one
Oh,
given 3
so we
times
have to do
and then
this.
the one from home.
Sorry,
3
Cassandra, couldn't make that out.
So the one given, vinegar given.
Yep, 3
3
times.
times,
And then the one you got in your house 3
and then
times.
the one, okay, got
Yeah.
it.
Yeah, because really, what did it take to do that? Like 5 minutes? So it doesn't take very long. It's the calculations are going to take. I mean, that's true of any experiments I've ever done. The calculations usually take 10 times as long as the actual experiment.
I have a crazy number for my mass percent and
Okay,
wondering.
how crazy? Run it past me.
Ooh, okay. Here, let me just write this out.
Let's put the whiteboard up and we'll see what's going on.
4, 8, 1, 5, 9.
So what was your concentration that you got?
0.080.
That was the molarity? No, that's not the molarity.
Where did I mess up?
That's the number of moles.
Oh,
You want molarity. Moles over liters.
now I'm all the way confused. Okay, let me go back.
So our volume of hydroxide times the concentration of hydroxide is going to equal the volume of acetic acid times the concentration of acetic acid. So our concentration of hydroxide is 1 mole per liter. And then our volume of hydroxide, we need to convert that to liters in order to get moles. So what was your volume of hydroxide you used? Should be around 4 or 5 mils.
5.2.
5.2?
Yeah.
Okay. So 5.2 mils times 1 liter over 1,000 mils equals 0.0052 liters. 0.0052 liters times that many moles. So that's also equals the same number of moles. 0.0052 moles of hydroxide. Well, that's also the number of moles of acetic acid you have. So what was the volume of acetic acid you measured out? What was the mass, first of all?
I'm sorry, the mass of.
Mass of acetic acid in grams.
Sorry, I'm sorting through my chicken scratch here.
Sorry, quick question. The moles, because it's a 1-to-1 ratio, the moles of acetic acid, the moles of hydrogen of the base, that's the same as the moles of the acetic acid.
That's right, 1-to-1
Okay.
ratio.
4.99 grams.
4.99 grams. So what did you calculate as the volume?
4.965 ml.
Right, because you did 1
ml.
ml over 1.005 grams, right?
Yeah,
So what was it? 4 point what?
99 grams.
4.99 grams. What's the volume?
Oh, 4.965 ml.
Right, doesn't change much. 4.96 ml.
Mhm.
So that's 0.00496 liters. So that's my volume, 0.00496 liters times the concentration of acetic acid. So if I move everything around, my concentration is 0.954 molar. That's my concentration of acetic acid. Basically, it's 0.00496 divided by 0.052.
Okay.
So this is my molarity of acetic acid, 954. So that means I have 954 moles in 1 liter of vinegar, right? 0.954 moles of acetic acid in 1 liter of vinegar. That's what that means. That's the meaning of molarity. Moles over liters.
Okay, yep, I'm following you. So then that
What did you get for a concentration? Molar concentration.
0.95, and I think I cut off one was the 4.
Okay, yeah. Okay. Yeah, that's fine to report that. But then when you're doing the calculation, you can carry more digits through.
And so that's so it'd be 0.954 moles multiplied by the molar mass.
Yeah, so you convert this part to grams of acetic acid using the molar mass, whatever it is, I can't remember.
Grams over mole, and then 1 ml over 1.005 grams.
Yeah, and this becomes that when you consider the density is 1.005 grams per mil. There's 1,000 mils. So 1,000 mils is equal to 1,005.
Okay. And then you convert it to liters, right?
So that gives me 57.29 grams of acetic acid over 1,005 grams of vinegar. Yeah, so you're a little high, but not too bad.
Okay. And then multiply that, by 100 for the mass percent.
Yeah. So you got like around 5.7%.
Mhm.
So, you know, that's not bad. It's a little high, but. So remember, that's why we do things in triplicate.
Where are we reporting the mass percent? Is that
I believe that is in table 1.
oh, table 1 has two pages. Okay.
Yeah, it's a big table.
Yeah. Okay.
Sorry, I'm getting kind of lost. How do you get the 3 numbers: mass of acetic acid in sample, calculated molarity of acetic acid in sample, and calculated percent mass of acetic acid in sample?
We just did the percent mass. So
I was
the
trying to do it
number-
myself, and then I started getting really confused.
So you just take the number of moles. So did you calculate how many moles of base you used? Moles of hydroxide.
Yeah,
Okay, so that's going to be equal to moles of acetic acid, right?
yeah.
So then just multiply. So your moles of acetic acid times the molar mass of the acetic acid in grams per mole is going to give you grams of acetic acid.
Oh, wait, you said moles of acetic acid times the molar mass of acetic acid
No,
will
but-
give you the mass of acetic
Yes,
acid in the sample.
right. And then you just divide that by the mass of the acetic acid that you measured in the first place. Should be around 5 grams.
Oh, okay. Because I thought it was divide, and then I was getting a really small number. I did moles divided by the molar mass.
No, that's why you never divide anything. Remember, you multiply. So your units cancel out. So then if you put grams on top, moles on the bottom, moles cancel out, and you're left with grams. Yeah, I never notice when I do these conversions, I never divide anything. I always multiply so I can see where the units go.
So I got 0 point. Okay, so when I did the for the mass, I got 0.23. And then when you divide it by the mass of the vinegar, that cancels out. And that gives the molarity, I believe.
No. Moles per liter is molarity. What are you actually calculating? You're calculating grams over grams. That's a mass percentage. So if you're taking grams of acetic acid and dividing it by grams of vinegar, which what you measured in the first place, that's the ratio of mass of acetic acid and mass of vinegar. Multiply that by 100 and you get the mass percent, which in your instance is 4.6%.
Is that bad?
It's pretty close to 5, right?
Yeah.
Yeah, so you're good.
So you want your calculated percent mass to be pretty close to what your mass of the vinegar is.
Why would it be different?
No, I'm just asking. That's what you want.
Of course. Yeah, I mean, you want to get close to the right answer, don't you?
Oh, okay.
Yeah. So really you should shoot for like less than, I don't know, 20% error. Anything less than 20 is pretty good. 10 is like really good and 5 is excellent.
Professor, I have a question.
Sure. What's up, Rachel?
So for like the data table number 1, what do we
Mhm.
put for the vinegar sample 2? Like the same? Vinegar
Exact same. Yep, exactly the same. So you rinse out your flask and you do it again. So you measure another close to 5 mils and you just do basically you just do the exact same thing. So we're doing triplicate replicas.
Oh,
Which-
and then for data table 2, that's when we use like a different kind of vinegar.
Right. So if you have a rice vinegar, or white wine vinegar, or if you don't have it, you know, you just have the same, if you don't have any vinegar at all, you can just use the same one. So most people have vinegar in the house.
Mhm.
I think we got like 5 different kinds upstairs.
Okay, thank you.
Yeah, so you can't use red wine vinegar, and balsamic vinegar, probably not a bad idea because it's black. And
Is apple
it's gonna be
cider,
kind of tough to see the color change.
apple cider vinegar okay?
Depending on how red it is. If it's super, super red, not so much. If it's fairly pale, you're probably okay.
Okay.
Yeah.
So my most of acid and base were 2 significant digits. So I guess should my mass of acetic acid and sample just be 2, or should it coincide with the mass of the vinegar in the way beginning?
So when you're reporting your results, report your results in the correct number of significant digits. When you're doing your calculations, use all the digits. So do not use rounded numbers to do calculations.
So just write as many numbers as I can.
No. When you report results, you report the correct number of significant digits. When you're calculating results, you use all the digits. So yeah, I don't want to see 46 digits on the table. But when you're doing your calculations, use all the digits.
Because the mass of the vinegar is 4.99 grams.
Okay.
So when I do mass of acetic acid in the sample based off the calculations of the moles and all of that stuff, I should use 3 significant digits.
Use as many digits as you want doing the calculations. But when you're reporting the result, that's where you figure out how many significant digits you should use. I don't know how to say it in another way, because when you say use, I don't know what you mean. Use like writing down on the table, or
Yeah,
use
writing
with
it down on the
calculations?
table, on the table,
On the
table,
use the right number of significant digits.
which
Your
would be
calculations, use all the digits.
which would be 3, because the mass of the vinegar initially was 3 significant digits based off of what I weighed.
Which number are we talking about?
Okay, so when you weigh the vinegar in the scale, there's 3 significant
Right.
digits, or 4. Well, okay, in this
3.
case it's 3. So on the table, when I do my data, when I write mass of acetic acid and sample, it should be in 3 significant. Okay, yeah, that's what I was thinking, because I get that wrong sometimes, so I'm just making sure. Either that, I'm just really tired because
So when you do your calculations, use all the digits. So how many? There's only 2 significant digits for the concentration of the base. So you could only report 2 significant digits.
for the molarity.
Now I'm doing it. Significant digits for the molarity of the vinegar. But you use as many digits as possible for your calculations of mass percent and everything else. But you only report 2.
That goes for percent mass too, then.
Right. Because that's based on the concentration.
Okay.
So we're sort of stuck with only 2 significant digits for the concentration, 1.0. Remember, use 1.0 moles, not one molar, 1.0
Right.
molar. Because if it was just 1 molar, we'd have only 1 significant digit, and this would, basically be.
So that's interesting. We're not really using the phenol. I can't even say that word.
Phenolphthalein.
Yeah, we're not using it today. Are we? I mean, I didn't when I put the vinegar and mixed in the base,
Well, how
I
did you
didn't-
know? How did you know when you were done?
because the pink.
Where'd the pink come from? Vinegar's not pink. Base isn't pink. Where'd the color come from? You had to have added the phenolphthalein, or it wouldn't have turned color.
Oh, right, yeah, okay, yeah, I did. Okay, I was. And then it changes color again too.
Yeah, if you add more acid, it'll turn back. And then add more base, it'll turn pink again. Let's keep going back and forth.
Oh, okay.
Yes, I wouldn't do all your calculations tonight. I would just like bang through the titrations as quick as you can, get all the data, and then you can analyze it tomorrow. But the first one, do the first one and see how close you got. That'll give you an idea of what volume to use. So the first, like I said, the first titration, it's going to take like 10 minutes because you're going to be slowly swirling. Next one should take 5. Next one should take 5 or even less. Yeah, just add 1 drop at a time. You should do okay. Anybody have any other questions about like actually doing the titration? All right, so what I'll do. All right, so chemical equilibrium. We're dealing with one in this lab. And the equilibrium we're dealing with is that acetic acid will dissociate when we put it in water and make H plus and acetate minus. So that's the reaction that takes place when you dissolve an acid in water. But this is a weak acid, and so it doesn't completely dissociate. So this reaction actually goes in both directions. But the reverse reaction is favored. So most of the time, if you have H plus and acetic acid in solution, they will go back and reform acetic acid. So at any one time, out of about 10,000 molecules, only 2 of them have dissociated into H plus and acetic acid, an acetate ion. And so we measure this equilibrium by a constant K. And the K tells us how much the reaction goes. Does it go mostly in that direction? Then it would be small. And if it goes mostly in the forward direction, it would be large, because we calculate K by what is the concentration of the products divided by the concentration of the reactants. That's how we calculate equilibrium. So at equilibrium, we would calculate or measure the value of H plus, the value of acetate ion, and the concentration of acetic acid that has not dissociated. And then that would give us the K equilibrium. And in our case, since this is an acid, we call it Ka. A just stands for acid. Kb stands for base. And so this number is very, very small. In fact, it is 10 to the minus 4.75. So the pKa is minus log of that number. Minus log of that number is 4.75. That is the pKa of acetic acid. So what that means is when I multiply the concentration of H plus and acetate and divide it by the concentration of acetic acid not ionized, I get whatever 10 to the minus 4.75 is, which is very, very small. That's where you get like it's about 2 in 10,000. That's where that number comes from. It's a really small number. In fact, I think it's even smaller than that now that I think about it. So every reaction has an equilibrium if it's reversible. Some reactions are irreversible, like when we combust something. So when you combust hydrogen gas in the presence of oxygen and make water, that reaction doesn't go backwards. That only goes forwards. It goes backwards if we add electricity. Then it'll go backwards. But we have to add energy to do that. If it's just left on its own, it will never go backwards. So that is a reaction that's not in equilibrium.
So a reaction in equilibrium is reversible,
That's right.
and chemical equilibrium is, I mean, I keep thinking it's the reactants equal the bases. I mean, the reactants equal the products, but
No, it's to get the equilibrium, you multiply the products, the concentration of the products divided by the concentration of the reactants. And so if the that's the equilibrium. So if the concentration of products is really small, that means that the reverse reaction is favored, that you have a higher concentration of products. If, on the other hand, the equilibrium constant is very high, that means the forward reaction is favored and you get a lot more products than you do reactants.
so chemical equilibrium helps you determine whether the products or whether the reactants, which
Which
one of
one's going to
it.
be a higher concentration?
Okay.
Yeah, that's determined by the equilibrium. So in our instance, with acetic acid, since this equilibrium strongly favors the reverse reaction, the concentration of H plus and acetate ion are going to be really small, really small. And you can sort of tell this because when our concentration of acetic acid that we determined is going to be around, let's say 0.9 molar or something like that, 0.9 molar. Notice that at the beginning of the titration, the pH was around pH 3, meaning the concentration of H plus is 10 to the minus 3. So the concentration, so at the beginning of the reaction, when we have an equilibrium, before we've added any base, my concentration of acetic acid is around 1 molar. And the concentration of H plus is around 10 to the minus 3 molar, or 0.001 molar. That gives you an idea of how great or how small that equilibrium is. We've only got about 1 in 1,000 acetic acids ionizing. That's why your Ka is so small.